Let's do one more impulse momentum example. This is example problem 3 from the chapter 9 slide notes. It's on slide number 53. In this case, a car is traveling at 20 meters per second. That's about 40 miles per hour. Crashes into a bridge abutment, and we're asked to estimate the force on the driver if the driver is stopped by, so let me write this out. What is force on driver of the car as the car comes to a stop? And part A is car stops by crashing into a 20-meter long row of water-filled barrels. And you'll see these usually at the exit ramp on a highway. You'll see sometimes a line or a kind of wedge-shaped distribution of big yellow or orange barrels, and those are filled with water to give them more mass to allow a vehicle that might be crashing to come to a gradual stop. So let's do part A first. Car stops by crashing a 20-meter long row of barrels. Okay, we're asked about a force. So we want to know what's the average force acting on the driver. We don't know the time that the car takes to come to a stop, that, in other words, the time that that force is acting on the driver. We do know the initial speed is 20 meters per second. And we know that it's coming to a stop, so we know the final speed is 0. Okay, we don't know the mass, is unknown. Okay, so at first glance here, this might look like you don't have enough information to solve this problem. But there's a clue here. There's another piece of information, and remember that we learned a lot of physics before we got to chapter 9. And that physics had to do with dynamics and kinematics. And so to solve this, we need to know something about the time. And time is one of the 5 kinematic properties that we use to solve how things are moving. And we know an initial speed and a final speed. So the other piece of information that we're given is this 20-meter long distance. So that is another kinematic property which gives us 3, which means we can calculate the stopping time as well as the stopping acceleration if we wanted to. So the stopping distance, x, is 20 meters. Okay, let's go after the time if we can, and the acceleration if we need to. So to do that, I'm going to set up my table of 5 kinematic parameters, as we learned how to do in chapter 3. The distance is 20 meters. The initial velocity is 20 meters per second. The final velocity is 0. What's the acceleration, and what is the time for that to happen? We have our 3 equations for kinematic motion. If I want to get time, what's the best one to do here? Let's see. Let's do, what do I have? I have x equals vit plus 1/2 at squared. I have 2ax is vf squared minus vi squared. And I have vf equals vi plus at. So the only one of these equations that has 3 things I know is the second one here, 2ax equals vf squared minus vi squared. So let's use that to get the acceleration, then we can get everything else. So 2ax is vf squared minus vi squared. That gives me 2a times 20 equals 0 minus 20 squared, which is 400. That gives me 40a equals minus 400. A equals minus 400 over 40, which is minus 10 meters per second squared. So that's the acceleration. 10, that's about 1 g. So that means that by crashing into those water-filled barrels, you come to a stop at 20 meters. That's about 1 g of deceleration, totally survivable. But what we need to figure out is what's the average force. Let's get the time from our other kinematic equation. I have Vf is Vi plus At. That means T equals Vf minus Vi divided by A, which is 0 minus 20 divided by minus 10, and that gives me T equals 2 seconds. So it takes 2 seconds for the car to come to a stop. So let's take a look at what we've got now. We are still looking for the average force, but now we know that the time is 2 seconds. We have an initial velocity is 20 meters per second, and a final velocity is 0 meters per second. If I want to use the impulse momentum theorem, that is J is delta P, or F average times delta T is mvf minus mvi. I don't have the mass of the person, and the only other piece of physics I've got is Newton's second law, F equals ma. This is essentially what the impulse momentum theorem is, though. If we go back and look at our notes from the definition of the impulse momentum theorem, it's really just Newton's second law. Newton's second law is basically just saying momentum is conserved unless a force is acting on a system, and it tells us how the motion changes if there is a force. So we're not going to be able to get the mass from those things. So I think in the problem it asks us to estimate the force on the driver. So I think in this case we're going to need to estimate the mass of a driver. So we're going to then, because let me just go ahead and write out what the average force is. It's mvf minus vi over delta t, and the final velocity is 0, the initial velocity is 20, so this gives me the average force is m times minus 20 divided by the time, which is 2 seconds, so that's minus 10 times m. So there's no way around it. I need to have an estimate for the mass. This is in SI units, so we'll take a mass of 70 kilograms. That's about 154 pounds. And that gives me an average force of minus 700 newtons. We already saw that the acceleration was 10 meters per second squared. That's about g. M times g is your weight. So the average force acting on the driver in this particular case is about equal to the driver's weight. Now, let's do the problem again, part B. If there is not that 20-meter long row of water-filled barrels, in this case, the driver comes to a stop by the 1 meter long crumple zone of the front of the car. So it's the same thing that we had before, except instead of the distance being 20 meters, it's 1 meter. So we're going to follow the exact same procedure. So I'm going to skip all that initial setup. We have 2ax is vf squared minus vi squared. X is now 1 instead of 20. So that gives me 2a times 1, or just 2a equals minus 400, or a equals minus 200 meters per second squared. So the velocity and, the acceleration and the distance to stop are related to each other. If I increase one by a factor of 2, I decrease the other by a factor of 2. So by shortening the distance to stop by a factor of 20, I increase the acceleration by a factor of 20. That is therefore going to increase the force by that same factor of 20. F equals ma. I'm just going to go straight to Newton's second law, and that's 70 kilograms, my estimate, times 200, which is 14,000 newtons. But the key thing is that 200 meters per second squared, rather, that's 20 Gs instead of 1 G of deceleration. And that's just because it took 20 times less distance to stop. So if you think about an example, a health-related example of football players who get brain damage from their head coming to a sudden stop, and they're wearing a helmet for protection. But really what matters is how much distance does ultimately the brain have to come to a stop, and there's nothing you can do. It's not like, is it soft or whatever, it's just kinematics, it's just basic physics. If you come to a stop in 20 meters, that's a nice gentle slowdown, and it's not going to be a big force exerted on you. If you come to a stop in a half of that distance, it's going to be twice the force. If it's a tenth of that distance, it's going to be 10 times the force. The only way that you can have physically a small force applied to the brain of a football player who is coming to a sudden stop, whose head is coming to a sudden stop, is if you spread that stopping distance out over a longer distance. So it's not like materials or anything like that. It's just literally, can I make a big cushy helmet? That's why airbags are useful. They're a big balloon, and instead of hitting the dashboard, and the dashboard compresses by a couple of millimeters before you come to a stop, that breaks your bones. You have an airbag, which is 20 or 30 centimeters, and you've got 30 times the distance to come to a stop, which means the acceleration and the force acting on you is 1/30 as much.